Cool. Well, so I'm Sean, and this is WebRTC, mostly the video bits. WebRTC is like this big protocol stack with a lot of moving parts, but today we're going to focus just on one part, which is just the video, and actually mostly just on the quality of service part. If you've ever used WebRTC, I'm sure you hear people complain, there was stuttering, I wasn't happy with the video quality. And this talk kind of explores like, why are those problems showing up, and like, how are people fixing them, and why is it such a complicated problem? So a quick is my background, like, why do you even care what I have to say? I work on the project called Pion, which is a collection of Go RTC libraries. So basically, instead of giving you a server, I give you the Pure Connection API in Pure Go. So just like in the browser where you can call, create user media, get user media, create offer, create answer, add track, you can do on your backend now, instead of deploying a full server. Like, the idea was I wanted to make something that you could have little building blocks instead of like a monolithic server. You can think about it like instead of running Nginx or Apache, it's starting an HTTP server in your C++ program. And we did this for other problems as well. So we made a turn server that works as an API, and then we also have a Ion, which is a cluster-based RTC system. So instead of having one monolithic service, it's made up of a bunch of Docker containers, and one of those is an SFU. One of those is for like what they call AVP instance. So it's like processing real-time media. So it does speech to text and other things like that. And then another is like a protocol bridge. And then the next project I worked on is WebRTC for the Curious. And it's a book. You can Google it right now and look through it. It's all on GitHub. And then we do markdown to HTML. And it's about the actual protocols, not just the APIs. And then it has history and also debugging. So that's my background and like my perspective on WebRTC. And this is really what it all comes down to with building live media experiences with WebRTC is just the constraints. So first off, everyone notices the quality of it. You can have a good UI, you can have great setup, but here's what people talk about at the end of the call. Like, the video freezes, the audio drops out, desynchronization, the quality fluctuates rapidly. You'll be talking to someone, all of a sudden their face goes real blocky, and then it comes back, and then you get disconnected. And what it feels like as an RTC developer, it's just this eternal struggle of quality versus latency. You get some great quality, but then it's 500 milliseconds delayed, and that's too long to have an actual conversation. So why does this happen? Just the truth is that the real world is cruel to us. Video is huge. If you have uncompressed video, 1280 by 720, you need 80 megabits a second. So that's obviously not going to work if you've got 5 people in a call. So what do? Then we have to compress them down using codecs. You've heard of like VP8, VP9, H.264. But all of the codecs, and we'll talk about this later, to compress video, you then make it hard to transport. It becomes fragile. If I'm sending uncompressed video, I send you all these pictures in a row, and it's okay if I lose one. But once you do video compression, you can't do that anymore. And then you have your network. So you have congestion, which means like, how much bandwidth do I have available, and how does the network respond? How do you figure out how much bandwidth you have available? It's a hard problem. And then errors. If you're on Wi-Fi, you'll have drop packets. If a gateway goes down, other stuff like that. So to give a background, as a quick background in video compression, I'm sure there's many people watching that know it better than me, for RTC developers, you kind of think about it in two ways. You think about your intra-frame compression and your inter-frame compression. So the one that causes the most problem is intra-frame. So if you have a bunch of frames that are in separate packets, and you break them up into 3 types. You have your keyframes, which is a full picture in one frame. You have your predicted frames and your bidirectional predicted frames. You have a lot of knobs here. You'll hear people say your keyframe interval and stuff like that. And here's a nice little visualization from Wikipedia. You have your iframes, your full pictures. You have your p frames that are just do a partial update. You have your b frames that are both ways. And then you have the constraints of real-world networks. And these are the big points I like to make to people. Is congestion isn't just about packet loss. If you have a network that can handle 40 megabits a second, if you send 50 megabits a second, you're not going to drop those 10 megabits. The networks, congestion manifests as both loss and latency. So some networks, if they have really big buffers, your UDP packets will arrive, but they'll arrive late. or some networks will drop them. It also can depend on like the behavior of every hop that you move through can have different behaviors. So let's say, you know, one person you're talking to in a call goes through level 3, another person you're talking to goes through Comcast. Like those hops in between can have completely different behaviors. One person can say like, hey, you're falling behind. The other person says, hey, like your video is blocky. It's completely different. And then jitter. Jitter is this fact that, like, again, just another attribute of congestion. Like your packets might not get delivered in order. They might get delivered in order but late. And then dynamic. The other thing that really hurts people is the fact that they assume that, you know, they can measure the network quality at the start of the call and that's it. But the truth is you're going to have more people coming on the network. You're going to have your, let's say that you start the call and someone else in the house is downloading something, then they finish. You don't want to constrain your call to 500 kilobits a second when all of a sudden you have 50 megabits available from the rest of the call. Like it's important to always measure and to realize that things can be changing. So how does RTC solve this, and like how does video transport work to get around these problems? So an important thing to remember with WebRTC is that it's over UDP, and there's a couple of reasons that does this. There's the connectivity part, which I think is out of scope of this conversation, but for us, the big thing is we want to perform our own congestion control, because we can't just send stuff over TCP, because I need that feedback. I need to know, like, is my video falling behind? Like how much is being sent? Like if I send it over TCP, like I'm just giving too much control to TCP. You'll see a lot of these things that people that do send video over TCP with, like, one example is RTMP, that, you know, you can try to do congestion control in the application and drop frames. It doesn't really work that well. You have variable latency and other problems. So everything over WebRTC goes over UDP, or at least we try our best. And then WebRTC, when sending media, you have two different packet types. You have RTP packets, which are to send the actual video, and you have these 4 fields that really make up the call. You have the SSRC, which is like your unique session identifier. So you have like your audio session, your video session, and maybe you have a screen share. Like each track has its own SSRC. And then inside each track, you have, you know, lots of sequence numbers. Think primary key, your unique IDs, and they roll over. You know, you have packet 1, 2, 3. You have timestamps, and then you have extensions. So I can send proprietary things, like I can like communicate the rotation or other things like that. And then you have RTCP, which are the control messages, and they're flexible, but a common subset is agreed upon. And these control messages will come into play later, but that's kind of how to communicate, like, hey, like you're sending too much, or hey, I lost this packet. So the first problem is, like, how do you fix congestion? What you're thinking about is, like, how much available bandwidth do I have, and then what do I adjust? So if I know that I have 50 megabits a second, what are the things I can adjust? I can adjust the bit rate, the resolution, the frame rate, and it's all of these attributes like that. And then, so how do we determine, like, who gives us this estimation? For RTC right now, it's actually an open question on what congestion controller I should use, and like how are they performing? So there is an actual group in the IETF, the RMCAT, where they're discussing and comparing all these congestion controllers, and they actually have a collection of tools that say, like, okay, this is how it performs, and they're being measured head to head. And there's an active conversation like this is still going on. You think, you know, RTP-based media has been around since the 90s, and we're still actively discussing this. It's a hard problem. So you have Google Congestion Controller, NADA, and Scream, and a couple other ones. And this is a way bigger problem, but just like the way I like to think about it is the BBR, which is a TCP congestion controller, has this really great picture. And it thinks about it in this way. You have startup, you drain, and you kind of measure, like, okay, this is my initial bandwidth. And then the congestion control has to run constantly and say, like, okay, I'm probing the bandwidth, I'm probing the round trip time, and trying to figure out, you know, what do I have available, because it's constantly changing. And then if you talk to anyone, they'll say, like, Google Congestion Controller is way more complicated than this. There's all these other things. And, like, I think this is like just a really good high level thing to get in your head and think, like, congestion is not something that can be measured once, and congestion is not just packet loss. It's also the round trip time. So we measure the congestion, we fix it. Like, now we're sending video at, you know, using the optimal amount of bandwidth. The next problem we have is the jitter. So when you're sending UDP packets, the ordering has not arrived. And so here's a visualization below. We set 6 packets, but 1, 2, 3, 6, 4, 5. So what do we do here? If we play out right away, the audio would stutter. You would hear me saying things out of order. But then it becomes a trade-off between latency and quality. If I delay too long, all of a sudden it's a very awkward conversation. If I don't delay long enough, then you have this breakup in audio. Okay, so now we buffer a little bit, but here it causes another problem. Now the timing is messed up. RTP packets, they don't have like an absolute timestamp. What they do is they just say the relative timestamp. This RTP packet I sent you lasts this long. So then over RTCP, we send sender reports, and sender reports map a relative timestamp to an absolute timestamp, and then we match them up. So there we've patched up our first problem. And this is the first time that we're going to start talking about RTCP, which is the sibling protocol that's over UDP to let you pass stuff. Okay, so now we're synced up. We fixed the jitter, but me and you are having a conversation over Wi-Fi, and we have 3% packet loss, and it's a terrible quality. The congestion controller is making sure we're not sending too much, but no matter how much we lower the bandwidth, the loss is unavoidable. And then the other thing to remember, this is a big point why we don't want to use TCP, is not all loss is equal. If I lose part of an iframe, it's way more painful than losing a little part of a P frame right before an iframe. Not all video frames are equal here. So there's 3 ways to fix loss. The first is reacting. So RTCP provides 2 different packet types to react to loss. You can do a NAC, which basically says, okay, you sent me 100 packets. Packet 97 I lost, please resend. That is the most effective one to do because it's requesting the smallest bit of information. So that's like the one you prefer to do. Now let's say you send me 100 packets and I lose 90%. Like NACs aren't going to help me. There's the round trip time is too high. I've lost enough. Let's just start the whole thing over again. We send a picture loss indication, which says like this stream completely broken. Give me a new keyframe. So now we start the whole stream over. We get a new keyframe, and we want to keep the keyframe interval low because we're wasting a bunch of bitrate on this stream where it's not needed. Okay. So, but there's other ways to fix loss. You can actually fix loss preemptively. So let's say you're sending 100 packets. I can send 5% of those packets twice ahead of time. Let's say I know that my Wi-Fi has this % of loss. I'll just send some packets twice, and I don't even have to wait for the receiver to send back that he lost something. There's less round trip time than NACs, but it's wasteful on bandwidth. You wouldn't want to do forward error correction if you're going over a perfect link, because then you're wasting bandwidth in the back. And then another step, and I think is really interesting for me, is fixing loss after decode. So if Chromium is one that does a really good job of this, is let's say you lose some audio, it will actually play the frame before, and it'll do all this extrapolation to figure out like, okay, what audio did I expect to be there? It doesn't even have to go re-request the packet. It can use other things like that. And I've never done this myself. I can't explain it that well, but it's a good one to call out, and it's a super interesting space. So next, like, those are all the problems that you'll kind of hit, and why this is such a hard space to be in. So next, like, this is all peer-to-peer. Like next, we haven't even talked about WebRTC servers. So WebRTC servers, the idea is that I send my video to a server, and then the server relays it out. It's kind of what we think about in the broadcast world, that if one person uploads to a server and then we have thousands of viewers over HLS, it's kind of the equivalent to that. I upload my video, and then thousands of people view it. WebRTC provides something called simulcast, which is the adaptive bit rate, but it'll do multiple feeds. So I'll encode my video 3 times, high, medium, and low, and then the server will distribute the high, medium, and low. So there's so the server doesn't have to run a transcoder or anything complicated like that. And that reduces the load on the server, and it means that, and it's the better quality because you don't have to decode and then re-encode and lose information in the process. And then you have another one, scalable video coding, which is actually layered coding. So you'll have one video stream that contains multiple qualities, and the congestion controller can peel back and decide like which layers to send. It's not as common. Browser support isn't great. I think that one of the big things with AV1 is you'll have layered coding from day one. So I think we'll see a lot better support in the future. So that was a bunch of information. And this is how I would summarize it when, if you're building an RTC project, is it's possible to ship without all of this. You can do like a high keyframe interval. Don't worry about forward error correction or NACs. Like just send a keyframe every 3 seconds and like ship your thing and show people how cool it is and then come back. And with that in mind, like there's always something you can improve. And there's so many people that get hung up and they don't ship and they're not able to get something out the door because, you know, there's always something wrong. And I think it's better just to get something out and then collect some data and iterate on it and go from there. And then the other crazy thing here that will drive you wild is you'll fix one specific thing. You'll move one knob, like you'll finally implement forward error correction, but then you realize that, oh, it just destroys your congestion controller because you forgot to take that into account, and all of a sudden you get all this interaction of components. It's a giant state machine that you have to keep in your head, and it can be very frustrating. And then the other one that I've learned the hard way is labs and demos are fun, but they're not very useful. A lot of network simulators are very deterministic. So you say like, I want to fix my bandwidth to be like DSL, and it'll set it like an absolute, and you'll be like, oh, it works great. But in the real world, that's not what happens. A user will be over DSL, but they'll have buffer bloat. So your congestion controller was completely useless because it didn't expect all this variability. It didn't expect, you know, the round trip time to matter, and that's a lot of things. So I think more and more, it's like how important metrics are. We already know this, but it's a lie we like to tell ourselves that we can like write it in the lab and it'll be all good. And then this is something I do at the end of all my talks that I really enjoy, showing like, here's some interesting open source projects that use WebRTC in the space. So WebRTC, you know, how it lets you send that video over the local network. This user actually built a Nintendo Switch that sends out via WebRTC right into an Oculus headset. So they've got this device sitting in their hand, and it's measuring the network quality and the congestion, and it's adjusting it so that it sends you the best picture quality, but using the amount of bandwidth you have available. And you've got that low latency since it's over UDP. And this wouldn't be possible with some other common protocols because you don't have all of those things available. WebRTC has the nice ability that it can do NAT traversal. So if you've ever set an RTSP camera, you think, oh, I have to make this available on the internet. It's not secure. Like, how do I do this? The nice thing is this open source project, Kerberos, they run a WebRTC agent in those remote networks, and then they send the video over the internet, encrypted and secure. So you can modernize all of these deployments. Cloud Retro lets you play NES games directly over the internet. So you run an NES emulator on that remote host, and then you send in your input via data channels, and you can play that game remotely. You can actually play it with a friend. You can save your game state. You see, there's a lot of paid products out that do the same thing, but this was an open source one that came out like when a lot of those things hadn't launched yet. Nico allows you to actually run a browser remotely. So you have a Chromium instance that's running on a Ubuntu VM remotely, and multiple users can control it. So my mouse clicks and movement are being sent into this remote VM, and now me and a friend can watch a YouTube video together. We can browse some documentation at the same time. It's super useful. The other one I've seen is the rebroadcasting of conference calls. So they'll join the conference call with Nico, and they'll send out the video feed. And so it's a conference call recorder, but you don't depend on like having to pay for a third-party product or something like that. Another thing that WebRTC is seeing a lot of usage in is in drones. So you'll run like a WebRTC agent on the drone, and it'll send the video back and forth. You can control it via data channels. It's super powerful. And then WebRTC, we talk about it a lot, like that it's a web-only protocol. That isn't true. Here's a program that's completely a terminal, and it's letting me talk from my web browser to my terminal, and we're sending those video frames back and forth. So we just have a VP8 to ASCII decoder, and it's pumping out all the frames, and it's being fed from a web browser. The creator of the cloud game then went on to make Cloud Morph, that lets you run applications in Wine on remote VMs. And latency is low. It'll adjust and figure out like what's the video that I have available and stuff like that, so you can get the best experience. And then WebRTC, it even just isn't a video protocol. It's also great for doing peer-to-peer communication of services. So instead of having to put a jump box on the outside of your network, because you're doing UDP, you can actually punch into these networks and have your laptop talk directly to a server without running VPNs. You don't have to install like an agent on your laptop anymore. A lot of times it can be frustrating. If you're on a new device that you're not authenticated with, you have to install an agent and do all these things. Like I SSH into my server just directly from my laptop, and I don't have to run a third-party service. And then one of the great stories with WebRTC is how, as we make this technology better, it helps others that need it even more than us. So Tor has a WebRTC censorship circumvention agent. So in the browser, it'll fetch a website via data channels, and then me running in a place where my ISP or government doesn't restrict access to websites, it'll forward stuff through. And same with file sharing. So if you have a file that you want to share from your desktop to your phone, they both support WebRTC. You don't have to depend on like emailing it, so it's unencrypted at rest and other stuff like that. And then in the VR space, especially, we talk more and more about with COVID and work from home, this can give you the ability to try to recreate those virtual experiences, and it's running all in the browser with WebGL and WebRTC. You can build these really cool immersive experiences and have the ability to prototype really quickly. And then this one's brand new. That's really exciting to me. Everyone here uses OBS. This project Lightspeed is a FTL to WebRTC bridge so that you can send your video directly from OBS into the browser. You can quickly stand up your own streaming solution and be able to broadcast to people and self-host. So I hope you enjoyed this and learned a little bit. Go check out WebRTC for the curious. A lot of stuff I talked about here is on there as well. And then feel free to reach out to me directly. If you're building something with WebRTC and you want some help, I'm happy to help. Pion is not a proprietary or commercial project. It's completely open source. It's a hobby project of mine that I'll continue to make better as long as I have the time. And thank you very much. And hope I have some good questions. And if there's anything that was factually incorrect about the talk, please speak up, and I'd like everyone to know the right answer. Thanks.